Well, hello, everyone. I'd like to thank the association for giving me the opportunity to speak today about fiber reinforced composites, or composites as we like to call them. And I'd really like to take a clinical overview. I'm, of course, Gerald Stark. I'm really not just a former engineer. I still consider myself an engineer. I'm an engineer, clinician, educator. And so I've always been interested in materials and strength of materials and how they work, but also how they don't work. And every material has a certain issue, challenge, not problem. They're just the physical limits that we need to deal with. And in O&P, it's always been so interesting to see how those work, and then frankly, how they don't work. So when we talk about composites, we're going to talk a little bit about what they are. We're going to talk about how they behave, what their identities are, and how they act to achieve what we want to in orthotics and prosthetics. So composites are some of the oldest types of materials. Composites are, in effect, nothing new. Concrete, which was really developed by the Romans. And when you go to the Parthenon in Rome, you can see the Parthenon actually feels, even though it was built over 2,000 years ago, it really feels as though it's a Disney recreation because it's in such good shape. That concrete that they created, which is a combination of cement and stone, is really impressive. And in some of the ruins you can see, in terms of archaeology, even from Babylonian times, the concrete they developed still exists, still stands today over time, because it really gets the benefits of both, that being cement gluing together the different types of stone. So in a sense, it's like very small level of brick. Even in England, you saw a combination of mud and sticks, mud and branches, created very strong Tudor type walls. We also see this in terms of the longbows, or even the bows created by Mongolian tribes people. They actually were a combination of different types of fiber, different types of branches. They usually used yew, which is very flexible but very strong and tough, in combination with animal sinew, which they would glue in a sense. And so they create this composite or layers of different types of components for the Turkish longbow or the English longbow to create very strong pieces. So this is a composite. A composite could also be steel. And then you can see on the far right, this picture of Damascus steel, where you see the ribbons of carbon that have been cold rolled, or actually cold forged, on top of one another. And this creates high carbon rigidity and then lower carbon flexibility. So we see these different ribbons. And so that's, in a sense, an alloy is a composite, in a sense, of two different metals. So what is a composite? It is basically, what do you think? Do you think a raft is a composite? The raft is a bit of a composite in that you have the different branches that are bound together with coconut rope from Lost. Is your grandma's Jello mold a composite? It still has the identity of both components, and it's quite delicious. So yes, it is a composite. How about that terrazzo tile in your high school? Yeah, that's a composite as well. How about the longbow, or the long boats from the Vikings? That's also a composite. So we have composites. The clinker type built took the different fibers of the boat and lay them on top of one another in terms of glue. So that indeed was a composite. How about Kool-Aid? Is that a composite that has two different materials? Well, it's not, because the sugar dissolves in the Kool-Aid ingredient. So I'm sorry. Oh yeah, it's delicious, but not a composite. How about the Jonas Brothers? Some might think that they're distinct, but it's hard to distinguish them from each other. So I would say they're not a composite. They're too homogeneous. Anyway, so a composite is basically two separate materials that have distinct properties and a matrix, and then a binding material of some type. And that matrix could be polymer resin, or the binding resin could be polymer resin, it could be metal, ceramic, and then a reinforcement that could be carbon fibers, nanotubes, plates, spherical particles. It could be basalt, it could be fiberglass, it could be nylon. But basically this matrix, which is the binding material, can be a thermoset or thermoplastic. So, and you know, in the old days, we used to talk about how acrylic was a thermoplastic, but it's kind of tending more, it's a spectrum. It's not one or the other is what I'm getting at. So a thermoset was polyester resin. You can tell the difference between a thermoplastic and thermoset, and that a thermoplastic will melt, whereas a thermoset burns. And so polyester, our older resin that was kind of carcinogenic, was a thermoset. You could really not heat that up and change the shape. Acrylic was a little bit more like a thermoplastic, but of course the resin was always limited how much it could move based on the matrix that was part of the fibers. And epoxy, which we use now, is a little bit thicker, and that's actually a form of thermoset. It's a rubber, in a sense, an artificial rubber. So in terms of resin, we use a combination of epoxy acryl so that we can get the workability of acrylic, which is almost like water, and epoxy, which really binds those together. So when we look at, in terms of a composite, a carbon composite, in terms of the bending curve, in terms of stress and strain, here you can see aluminum, here you can see steel, and a carbon composite is somewhere in the middle. And what we're looking for in a composite isn't necessarily stiffness necessarily. If we want stiffness, steel can probably provide that. If we're looking for something though that can bend and not break, and that's really a form of toughness, that's really what we desire. So when you look at something like skis, you can see all the flexibility that you're able to achieve with the carbon. The modulus, or the distance that the device deflects based on load, is very similar to aluminum. But here's the thing, carbon can be flexed quite a bit more over an infinite amount of time, and it'll come back typically. Now, there usually is a difference though with carbon fiber. As those little micro adhesions with the resin flex, it'll change its stiffness over time. So that's one of the differences. And you can see like little micro slices sometimes could help change the variable stiffness. And you can see just how much strain is being put on those two little carbon skis. When you think about it, it's just a really 1/4 of an inch that's riding on the edges. They make their turns. And so in prosthetics, we expect the same thing. Here's an earlier prosthetic design. You could see just how much we expect of that blade to flex, not just in the main keel, but also the heel as well. Look how much it flattens out. And of course, we want to do this roughly at about 1 million cycles, 1.5 million cycles per year. So when we test something for 3 million cycles, it's really just for 3 years of use that the prosthetic manufacturer is providing that, you know, liability coverage. And when we think about in orthotics too, it's flexing quite a bit. So it's not a matter of what we're locking out, it's what shape, what types of motions we're allowing. So when we look at things like making small cuts, we can see that this changes some of the inversion and eversion because we're removing some of those fibers. And you can imagine what happens if not all of those fibers are adhered to, or if over time there's small cracks that changes the flexibility of that material. And here you can see, I'll just turn this down a bit. Here you can see what happens when we apply a certain amount of load, the stress versus strain. Now here's something that in carbon prepregs that we find out is that we never really know how they'll perform until we actually make the foot or ankle or orthosis. We have to try them out, and we have to see what the fatigue strain is long-term, fatigue strength long-term. So we apply a load, we watch for how it changes. Even with the AFO devices, what we find is these AFO devices are prone to change their stiffness over time. So what we try to do in terms of engineering is preserve that stiffness even after 300,000 cycles. So we're always looking at cycles, we're always looking at stiffness. So one of the things about carbon that we use in O&P is we use a very specific type. It's SM pan carbon. Here, I'll go back to that. It's a specific type of carbon that's kind of in the sweet spot of stiffness, but also flexibility. And much of this type of carbon was engineered in Salt Lake City. Salt Lake City is in many ways the hub of composite prepreg and composite manufacture. And a lot of that has to do with Hercules manufacturing was in that area for aerospace. So that's why we see a certain type of carbon reinforcement used. You can see that other types of materials, e-glass has more flexibility and can enhance the carbon composite. The use of aluminum is fairly similar in terms of Young's modulus, but not in terms of the amount of deflection that can be achieved. So when we look at carbon composite, we want to look at this ability to withstand movement. So when we look at someone using an orthosis, we have to look at orthotic design, how many times it can lock, or how many times it can move. What we're trying to do is guide the movement more than locking it out. So we expect it to be much more dynamic. However, it's somewhat less predictable. We really don't know in terms of manufacture how it's going to interact with the patient until we make it. In prosthetics, sometimes we'll create feet that we think are active, but they're so flexible, they're probably better for geriatric use. Other times we think we're going to create something for geriatric use, and just because of the orientation of the fiber, it seems like much better for highly active people. So there is a little bit of voodoo in terms of design, in terms of how we move those fibers around. So some of the clinical uses of composites, again, are foot orthoses, prostheses, AFOs, KFOs, and KOs. The reason is it's so light, it's so thin, so flexible that we really can use this to really make a very close fitting device. Now, the downside is it's much more prone to certain types of things that could happen to it that disrupt those micro adhesions of the fibers to the matrix, or to the resin. The fiber matrix to the resin is so important, and carbon does not have a particularly it is smooth relatively. There's no cuticle. So the carbon that we use for lamination, cold lamination, is different than the carbon that's utilized for prepreg, for instance. The carbon that's utilized for cold lamination has an acrylic film to help it adhere a little better. Prepreg doesn't have that because it comes already with the resin imbibed into it. So materials in orthotics, we've used a lot of materials. Stainless steel and leather, thermoplastic, cold laminate, carbon reinforcement, prepreg composites, which are we have little patches of post prepreg composites with thermoplastic like polyethylene or polypropylene. And then these things can be used, or we can make the whole device out of that. And it's kind of interesting when you take a modern look at stainless steel and leather. Of course, those are older types of things, but they provided you both with the rigidity that you're looking for to maintain that movement, but also the flexibility of the interface so that you get this superior coupling of the device. So when we compare different materials, you can see there's somewhat, when we use composites, they're very impressive. Carbon is 84 times stronger than polypropylene, 250 times stiffer than polypropylene. Carbon is 4.7 times stronger than fiberglass and 34 times stronger than nylon. But carbon's not a perfect material. Carbon is very brittle. In fact, carbon by itself is not particularly ductile. So carbon has the least amount of strain. So you need to bind that strength of carbon with the resin matrix. So fiberglass is about 2.8 times less brittle than carbon. So this increases the toughness and flexibility. Toughness is the ability to bend but not break, just like a good football defense. Polypropylene is 2.5 times stronger than polyethylene. Polyethylene is 5 times more ductile than polypropylene. That's why polypropylene and polyethylene are utilized together. But really it's only, when you say co-poly, it's not 50-50. It's only about 5 to 10% polyethylene combined with polypropylene. So when we compare compare composite, thermoset, and copolymer, when we compare these, we just see that that the strength in thermosetting composite is so much greater than copoly, but then we preserve some of the movement when we use a prepreg composite. So stainless steel and leather, again, taking a modern view, it gives you a minimum amount of coverage. It's very adjustable, but it's not a particularly intimate fit, and it's considered uncosmetic and bulky. However, the leather does conform, albeit somewhat odoriferously, because it is porous, but it does give you that flexibility. It does give you that adherence or coupling to the shape. When we use thermoplastics, we get a much more intimate fit, but the strength goes down considerably compared to stainless steel. The thing about thermoplastics is because we cover the whole device, cover the whole leg, we have to recover some of that strength by the shape. So we're covering the entire shape of the leg, even though it's a lot less strong, to try to make up for the difference that we're not having just metal bars for uprights. Now we can improve that strength in certain areas. We did this for years with thermoplastic cookies or wings, or bat wings, we used to call them. So we put little pieces of carbon cookies in there, and we could increase that reinforcement, because at the ankle, that's where it's 4 to 7 times the body weight being concentrated in terms of strength of materials. And remember, plastic does suffer corrosion in the form of UV corrosion. You probably have seen this in your car in terms of your older dashboards, or maybe you've seen that where something's been left into the sun, or even modern, some of the modern plastic decks, they were not, UV protected. So that's one of the things that UV light, not just heat, but UV light breaks down that the plasticizers and the linkages between plastics. That's why some lower cost outdoor furniture gets kind of that dusty look to it. And you might use Armor All, which helps lay down those fingers, just like someone with hair sticking up. They use, some of that gel or pomade. That's really all Armor All does. And that seeps in and kind of liberates some of the existing fibers. So sometimes once you start using Armor All, you have to keep using it. So cold laminates are thermoset resin. Thermosetting resins can be epoxy. We hope that thermoplastic, we used to think acrylic was a thermoplastic, but it's somewhere in between thermoset and thermoplastic. And then we use reinforcing fibers like carbon, nylon, fiberglass, Kevlar. Now these have to adhere. Nylon has a nice cuticle that really saturates well, fiberglass as well, but carbon does not, nor does Kevlar. So we have to figure out ways to glue these together, and that's what the resin does. So prepreg composites are really pretty interesting because prepreg composites do not have excessive resin. With this previous cold laminates, my friends that are composite engineers used to kind of smile at our use of this. Originally, this was really to create air ducts for planes. Northrop Grumman used to use this, right? They created them out of plaster, and that's what people learned about and applied to prosthetics and orthotics. But it's not a particularly strong structural device. It's strong enough for our use, but it uses an excessive amount of resin. When you use that much resin, then there's a tendency for it to shear. So using less resin and increasing your fiber density is really the goal. And that's what prepreg composites come in, because they have the exact amount of resin for the carbon fiber. The perfect resin to fiber ratio is almost to the point of starvation. And in prosthetics, we just can't tolerate that. So we can't have half of our devices having starvation. So we probably put twice as much resin as we need to into the system. So when you string it tight, it usually increases the strength, not decreases it. So we use the prepregs have a very thin condensed layer, and they can either be into the carbon layers itself, or they can be sandwiched in with little cookies between this refrigerated resin that you can place and cut in between the carbon layers. This particular brace, this particular orthosis has a combination of fiberglass, e-glass, and a carbon. to create it. So when we talk about high temperature composite, which is really a true composite, the type of composite you have with your fishing pole, it's really with high heat and pressure. The high heat is in excess of about 450 degrees or higher, and usually about 6 to 8 atmospheres. So that's where you have to create a mandrel that's not made of plaster, because once you get above 370 degrees or so of temperature, plaster begins to burn. Have you ever seen that in some of your plaster mandrels? You probably have seen the plaster turn brown. The plaster is actually beginning to burn. So you have to create these on aluminum molds. And that kind of is a give and take, because even though you might make 6 different molds left and right, they may not fit perfectly. So they're not custom made, but they're made in multiple variations, and molds are expensive because they have to make the entire shape out of aluminum. So we give up a little bit in terms of intimacy of shape. So all those little pads all the manufacturers provide you really should be utilized to make a custom fit and create coupling. So the high strength of composites, we need to add sometimes more layers. Post pre-preg, which is this material here, which is a carbon with a peak LPET, I'm sorry, in woven into it, can actually stick to itself. So you can increase these layers and increase the stiffness, as well as you can repair it. So it's fairly easy to use. Some of the fiber types we have are E-glass, S-glass, Kevlar, carbon, Spectra, Dyneema, and these can be woven differently. The weave of the composite tells you more about what's happening. With most prosthetic feet, it's a unilateral, most of the fibers are in one direction, 90%, and then maybe 10% are just holding them in position. When you see a prosthetic foot with a weave on top of it, it's usually just a cosmetic addition, so that it looks like a carbon weave, but most of that prosthetic blade is actually unidirectional fibers of carbon. So carbon, how is it made? Well, it doesn't come from carbon sheaf. There's no carbon tree. It's really a polyacrylonitrile, which is similar to a type of glue, acrylic glue, super glue, that's spun into a very small thread and baked repeatedly. And this is a typical carbon fiber that's about 6 microns, and that's the human hair right next to it. So these filaments are exceedingly small, and what they do is they're repeatedly baked, and the nitrogen bonds with the carbon are baked away. So all that's left with it is truly carbon. So in terms of fiber strength, here's where you see that Kevlar is 5 times stronger than steel, Dyneema even stronger, which is 15 times stronger. So carbon is fairly strong stuff when you get down to it. Even a spider's web filament is actually stronger than steel in terms of the size of skein that it is at the smallest level. When we look at the modulus of elasticity, this is where you see carbon's modulus. E-glass is much better. Carbon's much more brittle. Spectra is close to it. So we usually use combinations of those two. Spectra is about 33% lighter than Kevlar and 10 to 15 times more abrasion resistant. So that's why you see Spectra, or Dyneema, the trade name, used in some of the gardening gloves. Dyneema also wets better. So sometimes we use Dyneema more than Kevlar at the present time. Carbon orientations are also important, as I mentioned. There's unidirectional, which is 0-90 bidirectional, unidirectional or 0-90 bidirectional, or a 45-45 braid. And this is how they're knitted. The thing is that the way you see the opposition to the movement of direction, you have to understand that the 45-45 is not the way you see it braided, but different. For instance, if you look at this plain weave, there's plain weave, which is every other fiber, and then twill, and then a satin weave, which is 1 to 5. This also influences the amount of resistance that the weave is taking on. So this is what I was getting at. A 4x4 twill is better for draping, and a 2x2 twill is better for wet lamination. So the 4x4 really has longer stretched fibers for prepreg. So those weaves are a little bit different. So when you ask someone about their prepreg, ask them about the type of weave they're employing. When you look at the fiber directions, this is unilateral. So for instance, you'll see most of the fibers in one direction with maybe a fiberglass or nylon cord that's binding these together so you can use these. If we have a 0-90, we have a medium bending strength, medium torsional strength. So we're increasing that torsional strength a little bit more in the opposite direction. And then the fiber direction, this is what I was getting at with the 45-45. Know that it's actually, the resistance is in the direction of 0 and 90. So it's actually at 90 degrees from where we think it is typically. Many people think that the direction is bidirectional by looking at the weave, but it's actually across the matrix in a sense. Here's the thing, if you get this wrong, if you get that weave wrong and how you lay it up, you decrease the strength by quite a bit. So when you look at this weave, you have to look at how much torsion do you think you're going to get, how much bending, and how much you're getting in the 90-degree bend. So that's why we typically use 45-degree twill or 45-degree weave when we're talking about prosthetic wet lamination. In orthotics, we have to do multiple things because there's multiple torsions, multiple levels. So they typically add 5 different layers to accommodate for those different movements. So the thing is, the reason we worry so much about this weave and the angle of the fiber, if we have just 10% deviation from the load direction, we decrease that load strength by 38%. So if we're off just a little bit, it makes a big difference. So how do we accommodate that, or how do we get away from that? Well, we do multiple levels or multiple layers that provide us resistance. So we know that we're accommodating the range of motion. So if we have 23 degrees of rotation, for instance, we need to accommodate for those 2 different positions with the lower limb. So 23 degrees of lower limb movement in terms of rotation, we need to make sure we have fibers that can resist those extremes, or at least 80% of it. So fiber reinforcement is really important too when we're talking about foot plates for orthotics, because majority of them break at the metatarsal. But that's why we want to always do a toe lift of some type if we're doing prepreg, so that we're kind of creating that rocker bottom for like on a prosthetic foot, because what we want to achieve is as little deflection as we can to increase that level of stability. Thermoplastic resins also come in a wide variety, although many of them we no longer use because there's certain ones that are safer. Polyester, acrylic, modified epoxies, and epoxies. Modified epoxies, blended epoxy with acrylic to get those together. In terms of polyester resin, that was very inexpensive, but much more dangerous. We had that, it was a phenylalanine that we used to use, polyphenylalanine. This is the eyedropper that we used to use. And if you mix that with catalyst, it would create a big spark, but it was also cancer causing. I remember we used to use this at Northwestern, and when I think about 18 different legs being made simultaneously, being laminated, I hope that we had adequate ventilation. Yeah, but it's somewhat more dangerous. But it did have good workability in that it wasn't too, it was slightly viscous, but not too viscous. And it was very predictable. Yeah, I'm sorry, diethyl-aniline was the promoter. And if 10 cc's soaked through your skin, you'd have permanent liver damage. So this was very dangerous, and the vapors as it was curing, once it was cured, it was fine. But if you had mixed too much or too little of the hardener, what would happen is that, sometimes people would say, I don't measure it, I just give it 2 good squeezes. If you didn't mix enough hardener in, then it would continue to cure over time and cause some chemical exposure issues. Acrylic resins were much more safe. It was more like a methyl methacrylate, kind of like a super glue, acrylic monomers, and it just used a catalyst and peroxide. It was still somewhat reactive and smelled pretty poorly when you talk about seagull hearts in the morning, I remember. But technically it was not very, although it was noxious in terms of the vapors, it was a little safer to work with. Um, but it was pretty high cost, not a very forgiving in terms of movement. So it was somewhat more like a thermoplastic, and some of the gas liberated during the, the polymerization cycle, and it was very UV resistant, but this particular acrylic that we used in lamination was pretty watery and difficult to work with. Epoxies is a form of rubber glue in a sense. It was cured with triethylamine, triethyl and this was also somewhat dangerous if the stoichiometry or the mixture was not predicted accurately. And so then we got into, and it was fairly thick, so we try to water it down with acrylics. And so that's when we got into the modified epoxies, and that was also cured with a catalyst. So it's a thermoplasticky thermoset, so it's somewhere in the middle. So when we talk about composites, it's important to remember it's not one or the other. This provided good adhesion and also good saturation. So it tried to give you the best of both worlds, epoxy and acrylic. And now I think we're even improving the types of acrylics that we have. This is an LPET polyethyl, polyethylteramine. This is where you can see that it just becomes a plastic. And so that plastic can be combined with composites. So you get this great adhesion, but you can, because it's called a post prepreg, you can remelt it in a sense. If you don't over melt it and over mush it around too much, you can preserve most of the strength. And this is where you have enhanced pressure techniques of the resin. As I mentioned before, it's typically 550 degrees is 6 to 8 atmospheres. And that's why we can't use plaster mandrels, or at least if we did, we could only use it once. But it's important that you have really no vapor, no water in that, because it creates bubbles within the system. So that's typically why aluminum is used. And so when we use prepregs, we try to make sure that we accommodate all the possible fiber orientations or resistances to the forces that we need to. So when we're laminating, we try to make sure that we don't have any voids. We try to make sure we wet everything completely, and we need to avoid any sort of debonding or crazing, because once the resin breaks down, that's the real challenge with composite. Once you see voids, once you see cracks, then they'll begin to propagate, just like cracks in your windshield, right? And unless you bond them, they'll continue to propagate, and that's called crazing. So when we drill composites, it's important to really use very sharp tools. When we use composites, make sure we use the tin oxide type gold coating of the drills that we use for metals, not necessarily the dull wood drills. We need to avoid excessive heat. And then when we do cut composites, it's important to almost burnish or polish the trim lines so that you don't get any edges, especially at the ankle. When we grind composites, one is to protect yourself. These guys aren't really using any sort of masks, but you need to protect your skin, and maybe you protect your skin by putting a stockinette over your wrists to prevent carbon from working its way into your skin. And another issue is that the composite dust can get into your lungs, and because carbon is really not biodegradable, it just stays there, and it just stays within your mucous membranes if it makes little slivers into the side of your lung tissue. So when you use a cone, it's important to use a very sharp cone, and one that's lubricated with silicone. And then also using fillers, sulcoflock, which is really a refined cellulose flour. It's a cellulose fiber, gives it some dimensional stability, but very little strength. Microspheres also provide a bit of strength to fill these voids, but it gives no strength at all. It's used to fill the voids. It's not for compressive strength, maybe some tensile resistance. But again, both of these materials can also create small slivers and are not biodegradable. So you have to be very, very careful with all of these types of devices. And so in composite manufacture, it's really important to observe some simple rules. One is in modification. Modify as normal, but it's even more important to keep your mold, your plaster very smooth, and to delineate these trim lines very carefully, because you're going to actually smooth them into shape. And then another thing is to really make sure that the mold is thoroughly dried, to use stockinette. Make sure that if you don't do this, then the composite will not adhere. Moisture is bad. Here you can see where a composite was exposed to moisture, and what it does is it steams the matrix. And so when it steams the matrix, you get some of this porosity, and this is where things can be broken over time with fatigue strength. Here's where you can actually create a mandrel with multiple holes, and you can blow the water out to get kind of to remove as much water as you can. So it does create these micropores within the plaster, but if you coat it with a separating balloon, it should work quite well. And then using special materials, like you can't use the same old PVA bag you utilize. You might have to use a nylon type that's rated to over 500 degrees. And then using silicon sheeting, silicon separators to help lay that up. And so when we talk about strength of materials in prosthetics and orthotics, we talk about this cantilever beam, and this goes back to my design years when I was an engineer. But we really look at trying to make sure that we preserve the strength. So we have this modulus of elasticity, the thickness, the beam width. And so if we can expand that shear resistance, then we get more resistance. Orthotics is really a tough one, because at heel strike, you have compression at the behind the heel at the upper heel strut, and then tension that's building on the anterior. And then when you go to heel off, now it's compression and tension is reversed. This gives us a really tough design issue, because we have this constant pushing and pulling. And that's why in orthotics, because it's not a complete circle, we have to have a way for them to get into the orthosis. We create kind of it's an inherent design challenge for us. And that's why typically you'll see breakage at the metatarsal heads. You'll see it right at the ankle, because of this constant pushing, pulling, and bending. So this cross-sectional strength, you can see some of the shear. It's also dependent on the thickness. In this case, we increase the thickness where, again, this is where it harkens back to our understanding of metal bracing. We increase the resistance. We can either sandwich in or create a corrugation for orthoses. So this increases the amount of resistance and increases strength. In this case, this was an improper fiber placement, and also there was not a toe lift in the casting. So what we see is this breakage at the metatarsal head. This is not uncommon for composite, and normally the orthotist doesn't necessarily blame themselves, but they do have to look at how they took that impression. Did they take it differently, or did they give you a plank in terms of the ground reaction force? So they really need to create that roundness of movement if you want to preserve that. And also we do increase toughness by increasing the amount of dyneema in that area as well. And then this is a custom layup where you can kind of create your own based on a post pre-preg. So this is where this adheres. In this case, there was not enough resin. You can start to see the carbon and LPET stick through. Yeah, I'm sorry. LPET is actually, LPET is polypropylene terephthalate. Yeah, and so excessive heat can also create these globules of resin as well, and uneven heating. So all of these things contribute to carbon composites not doing as well. Sometimes when we look at lateral versus medial uprights, we can look at see how that influences this walker, who happens to be Carl Fillauer. You can see that there's a change in movement based on if someone's a supinator or pronator. But you can see in this case how a carbon beam, a cantilever beam, is helping to either mitigate or attenuate some of the movement, or it's in some cases doing nothing at all. So it's really about placement. So we're really seeing custom carbon AFOs becoming a little bit more like prosthetics in a way. We have the coupling of the interface with a nice fitting, and then we have the reinforcement of the custom carbon. So hopefully we talked a little bit about carbon composite, how they're different, what the natural differences between them are, how we can maximize their use, and hopefully become a little bit better in terms of what our design needs to change and how we work with them. So it's really important to polish them, any sort of edges. I know one of my friends, he likes to put a masking tape on his fingertip and rub the edge or burnish it with a little bit of super glue. And he finds that that helps keep the fibers laid down. But anytime you see a crack propagating, you need to monitor that. If you do these things right, carbon composites can really fit the patient better long-term, provide something very lightweight, very flexible, give you the strength of metal, give you the open shape, and also the conformance to shape of plastic. So I thank you for your time. I hope that was beneficial to you, and I hope to see you again soon. Thank you.